Hi, let's do an ANOVA with our tweet engagement 2 data. We've done a t-test on this. It's exactly the same. We do it exactly the same way. So fit y by x, analyze fit y by x. We then put engagement score in y response and tag status in x factor as we did before. And then it gives us this. Is there a difference there? Let's have a look. Means ANOVA pooled t-test. So there we go. Now we can see it gives us our t-test, and the p-values are exactly the same, 0.11. They are both, those p-values are transformed from in this case for t-test for the t-ratio. But what we're more interested in is this here, the f-ratio. So it's just another way of deriving the same results. But we're using an actual model here. So it gives us a little bit more information. We lose the directional aspect of it. So whether it's two-tailed or one-tailed, whether it's greater or smaller, we lose that. But we can, you could argue that you don't need that when you can see the sample means, and you can see that they're different, so you can make a directional inference if you want to. Anyway, that's not important. What is important here is we've got the ANOVA table, which is not, it's compared to the previous demonstration in the lecture, or in the mini lecture. The numbers are a little bit messier. The numbers are not quite as nice. However, what we have there are the total sums of squares, which is at the bottom there, the sums of squares of the model and the sums of squares of the error. Okay. However, to get the mean sums of squares, which is what we're interested in, we divide them by these degrees of freedom. So the degrees of freedom very quickly for tag status is the number of groups minus 1. For error, it's the number of observations minus the number of groups, which is 30 minus 2, which is 28, and then the total is 29 degrees of freedom. Now, without dwelling on that too much, we divide the sums of squares by 1, and we get the same value. Divide the sums of squares of the error by all of the different error, opportunities, the interactions within the model. So we get 230 divided by 28 is 8.230. Right, all very good. And so what? This gives us our F ratio. So 109 divided by 8.230 gives us our F ratio. So in that case, given this model, given the size of the sample and other various factors, it translates to this p-value that we've already discussed here. So that's how the ANOVA table produces a p-value. This little jump here I haven't explained. Let's just you just know that there's a specific mapping based on sample size and variation and sort of statistical proofs, which we don't really need to go into. Just think about high F ratio means a low p-value, generally speaking, and yeah, just as a high T ratio, a high T statistic means a low p-value. You can also look at the confidence intervals of the means that you might want to talk about there. So there's our sample means, 24 and 27 are confidence intervals. So that's, we don't know what the population means are, but we are 95% certain that they're between 22 and 25. For hashtag equals no, and 26 and 29 for hashtag equals yes. So that's what you can report on. R squared, what this is, it's the variation, as it says there, as I just circled on it. The variation in response is attached to, or is caused by the model. Okay. So it is 0.32. So 32% of the variation in our engagement score is down to whether they've got a hashtag in or not. So there are other reasons for variation, but we don't know what they are at this stage. There's 68% unexplained there. How this R square is calculated. That is the sums of this here, 109, the total sums of squares the model sums of squares, which is 109, divided by the total there. So that gives you 109 is about a third of this total of the errors. Okay, so so yeah, I mean we've got more. There's unexplained. There's more residual than model, but we can still accept it as a model. It still stands. And there you go. Right. So that is our ANOVA model. To test the assumptions, let's do the easy one first because you've done it before. We did it last week. Unequal variances, you just do exactly the same thing. Just click down on the red button, click on unequal variances, and then it will, oh yeah, it produces this output here at the bottom. All right, and just as we did last week, you can see the standard deviations are small. But a formal statistical test is for equality of variances. The null hypothesis for all of these tests is that the variances of these samples, and the populations rather, the variances within the populations given these samples are similar, okay, are very similar, and this allows us to state that. We can't reject the null hypothesis for equal variances, so we're great. Okay, so we've got equal variances. We don't need to use this Welsh test output here. We don't need to. You need to use this when, unfortunately, when this comes up all red and small values. When the variances are not equal, then we turn to this interpretation for the overall model. And it's not as robust, but it is what it is. Anyway, in this case, we don't need to worry about it. So there we go. Now, the other slightly more tricky one is the normality assumption. It's a little bit different in this case than it was for t-testing. You can't just look at the sample data and test it for normality. It's around the errors. It's around the residuals. It's around, see the mean value, which is right in the middle here. It's all of the differences between these guys and the mean of that, which is 24, what is it, 24.09. And for that one, it's something like 20, well, what does it say, 27.9, so nearly 28. That value there, that line in the middle. So what are all of these, if you take all of these differences, are they normally distributed around that mean? How do we calculate that? Okay, this is how we do it. So first of all, I click on the sort of drop down and I click down to save, and I choose save residuals. So I'm not doing save script, remember, I'm going to save residuals. Now what does this do? It does nothing to this output here, but what it does do, if we go back to our table, which is here, you'll see it's added in this strange extra column, which is called engagement score centered by tag status. All that is it takes the mean value for hashtag. Let's start with hashtag equals no, for example. The mean is 24. 24, give or take, shall we say, a few decimals. We'll say it's 24. So that's a nice easy one. So you can see that Martha Lane's engagement score for that particular tweet is very similar. So 24.403. So her residual is 0.3. See, it's just a little bit higher, Her next one down is a little bit better, 24.6, which is 0.5 higher, so on and so on and so forth. Some cases it's less, all right. In some cases it's much bigger. So hashtag equals no. So that one is 27.9, so 28 nearly. So that's nearly, you've nearly got a residual of nearly 4 there. So these are all the residuals, the errors, okay. Now, and in different examples where the model is not as strong and there's more variation, you're going to get at least bigger spreads of values here. So all we do is we do a distribution analysis of that engagement score centered by tag status and run it, and we get this. Okay, let's just like that. Whoop. Bring it back. Where have you gone? Where have you gone? No. No. There it is. Right. Okay. So there's a distribution of the residuals. See. So remember that obviously all centered around, virtually around, more or less around zero. More or less, given for rounding up. That's a tiny. Suppose it should be zero. That's what that, well, effectively it nearly is. Anyway, so we do this normal quantile plot, and then we can interpret our normality of residuals. Now, what you might want to do in the assessment is do it formally, do the Shapiro-Wilk test, goodness of fit. But we can see fairly emphatically that these are normally distributed residuals. So we're good. We are good to go. So this model is absolutely fine. So we can just, we can report on it in all good confidence and in all good, it's all good. So there we go. So there is an ANOVA, a two group, an ANOVA with two groups looking at the residual and with a focus on the residuals, on the focus on the assumptions. Sorry. Okay, right. Bye bye.